Hello, I'd like today to talk a little bit more about certain specific values of logarithms. So last semester, we discussed how certain numbers were irrational, and we showed that you could prove certain numbers were irrational, right? So we remember that, for example, we showed that root 2, the square root of 2, was irrational, and we did that using the rational root theorem. Rational root theorem. Okay. The rational root theorem let us show a whole bunch of numbers, a whole class of numbers were irrational, okay? Because they had associated algebraic relationships. In this case, we looked at the polynomial x squared minus 2. We set it equal to 0, and we said the rational root theorem says that the only possible rational solutions of this have to be plus or minus 1 or plus or minus 2. And then we said, hey, wait a second, none of those are root 2, but root 2 is a root of this, so root 2 better be irrational. And we generalized that a fair bit. We would now like to talk about logarithms. And if you've been playing with logs a bit at this point, you'll notice that a lot of the log values on your calculator look pretty ugly. You'll have lots of decimals going after the decimal point, lots of different numbers. Are they rational? Are they irrational? Maybe they're all actually nice rational numbers, and we just haven't gone out far enough to see that they're rational, that they actually have nice ratios. So let's convince ourselves that some of the log values we've seen really are irrational numbers. Let's look, for a start, at log base 2 of 3. All right. So by our change of base rule, we know that this is also ln3 over ln2. That doesn't make it rational. It's a ratio, but this isn't a ratio of integers. So it's certainly not the case that natural log 3 or natural log 2 is an integer. So we just need to think about this a little bit more. Maybe it's rational, maybe it's irrational. Claim log base 2 of 3 is in fact irrational. Here's how we're going to prove it. We'll assume that this number is rational, and we'll use our rules of logs and exponents to get a contradiction. So assume log base 2 of 3 equals a over b, where a and b are positive integers. This is the same thing as saying 2 to the a over b equals 3. And it's a rational number such that when we raise 2 to that power, we get 3. Here's what we're going to do. We're going to raise both sides of this equation to the b. So this is going to become 2 to the a over b to the b equals 3 to the b. And we're now going to use one of our exponent rules. So this becomes 2 to the a over b times b equals 3 to the b. These cancel. 2 to the a equals 3 to the b. And now we should see a problem. My suggestion is that you pause for a moment and think about carefully why this equation is bad. So pause. Okay, did you come up with a reason why this equation is bad? Well, this side is even, right? This side's a power of 2. This side's odd. That can't happen. Now you might say, well, wait, how do I know this side's even? Maybe a is 1. rather a is 0, then this side would be 1. But that can't happen, right? Because in that case, I'd have 2 to the 0th equals b, 3 to b, fine. But we assume these were positive integers, so that's definitely not our circumstance. Even if we hadn't assumed they were positive, it'd still lead to an issue as long as b, there would be issues. You'd have to have 0 over 0, and it's not good. But the point is, this is bad because this side's even and this side is odd. Okay, so we have a contradiction. An even number can't be an odd number. Even number can't be an odd number. All right, so our original assumption that this was a rational number had to be wrong. This same argument, at least, will work just as well if I replaced my 3 here with any other odd number greater than 1. Log base 2 of 5 would be irrational. Log base 2 of 7 would be irrational. Log base 2 of 9 would be irrational, and so on. So that gives us, at least in a very limited sense, a big set of irrational numbers to work with. But those all involve just log base 2. Can we go any further? Yes. All right, so I'm going to erase a bit. I'm going to make a slightly broader claim. All right, and this claim is going to be followed. Claim log base p of q is irrational whenever p and q are distinct prime numbers. Okay. So remember, a prime is a number that's just divisible by 1 and itself and is greater than 1, right? Primes are examples like 2, 3, 5, 7, but 9, for example, is not prime, it's 3 times 3. Okay. So let's follow the same sort of argument we made earlier. So we're going to assume log base p of q equals a over b for positive integers a and b. This is the same thing as saying p to the a over b equals q. We'll raise both sides to the b. P to the a over b to the b equals q to the b. P to the a over b times b equals q to the b. Using our exponent rule to bring that in. The b's cancel. P to the a equals q to the b. Now, we don't have as immediate a contradiction of just from even and odds, right? Maybe p and q are both odd, for example, right? 3 and 5, p could be 3, q could be 5. But I claim this equation is still bad. And the reason for this equation is bad is unique prime factorization. Right, actually, let's call it the fundamental, we refer to as the fundamental theorem of arithmetic. And that says positive integers have a unique factorization as primes, into primes. Right, 105 is 3 times 5 times 7. Right. So, for example, 105 is 3 times 5 times 7. That means there's no other way to write 105 as a product of primes, except in order. It can't, for example, be 11 times 13, okay? And so on. So prime factorizations are unique. But now I have a number here, p to the a, which has 2 different prime factorizations. One is p to the a, one is q to the b. So FTA says this is bad. So again, we've reached a contradiction. So our initial assumption that this was rational has to be false. So a lot of those numbers you'll be plugging into your calculator when you calculate logs really are irrational numbers. And it's not that if you went out 100 places, you'd start seeing a pattern. They really are not repeating. And so when we need to use them for practical purposes, we really are going to have to rely on approximation.